That's a good thing I styled my hair this morning, though.
Okay. What are we doing people-wise? Looks like it's gotten rather stable here. Want to go ahead? I guess I'll be moderating this session and just making sure we kind of stay on time and just introduce the presenters. And I think we're kicking off with Dr. Colin Klein, who just recently joined us, less than a year and a half ago, right as we entered the COVID era.
Right.
And Colin's found a way to stay very active, and particularly with anything that could involve computers and remote connectivity and so forth, and has actually done a really tremendous job in a collaborative effort with Sam Kotler and Savannah Shoemaker in developing some new tools we'll be using at NCATS relating to quantitative NMR. So with that, Colin, I'm just going to turn it over to you.
Okay, thank you. Yeah, like Alex said, just want to give some special thanks up front to Sam Kotler and Savannah Shoemaker, who are part of the analytical chemistry core at NCATS. Without their help, having really no chance to really move this forward like it's happened. So, so just to sort of give a broad brush of how this entered into something that we were looking at. So the traditional synthetic organic chemistry workflow has three sort of overall phases in terms of designing the reaction that you're going to do, executing, and then doing some post-reaction processing. And there's all these different stages that have different aspects of them that have to be worked out. And that's why PhDs in chemistry take a long time. But there's a formulation, there's a templating, setup and implementation, reaction progression monitoring. There's usually a quench. There's some material recovery. There's often a first pass purification, and then a final purification analysis. And so there's details involved with all of these phases and stages. And so how are we going to understand how these are progressing based on what things we've selected with that? And so in general, the overall sort of learning strategy is to do some benchmarks. So these are a set of reactions that we're using to understand how each of these phases and subphases are working. So you saw the slide yesterday from Alex. There's a short list of chemistry benchmarking. There's a total of 12 reaction types, and we do 2 reactions each. And then so constructing a workflow for each of these benchmarks. With templating, we might think about which reagents are in excess. If there's a catalyst involved, what kind of loading, concentration, whether we're going to do batch versus flow. So that, with these sort of break marks, I've indicated, what the general focus of my work might be. Purification analysis will be more on the analytical side of things. The formulation and templating might be more on the informatics side of things. Of course, what I do in the middle will inform both the purification and the informatics, and vice versa, right? So they'll also inform how I choose to do things. But overall, with the chemistry, we have multiple objectives, and just not just yield. There might be selectivity for different diastereomers or side products. There might be impurities, conversion, cost, time, reliability, throughput are also objectives that we'll have. And all of those things will inform how our work streams are set up, whether it's the implementation method development, different automation choices, system integration, like I mentioned with informatics and the reaction prediction and templating, and then purification method development. So, cost, time, reliability, throughput, those are things that you can kind of understand outside of the lab, but yield, selectivity, purity, conversion, impurities present are something where we're going to need to have some well-developed analytical techniques to get that. So and in the context of that, this is all about making improvements. So whatever cycle you want to use, design, build, test, design, make, test, analyze, plan, do, check, act. We need some information about how we're going to make improvements. So looking at this again, this overall generic templating of a reaction, we might have this amide coupling with some different annotations about roles of reactants, reagents, additives, concentrations, byproducts. And when we set things up, we have different material / mass flows, right? So in the implementation phase, we're adding reactants, reagents, and solvents. We add a quench solution. We might have some mechanical losses from imperfect transfer or recovery. We might do some extraction solvents. A first pass purification will remove impurities. And we'll add some solvents. In most cases, that would do a first pass purification. So trying to understand how everything is working in this core phase, just based on yield, is not really a sustainable, or I guess I should say, it's not really informative of what's going on here. So we really need to understand some quantitation at these different phases. So we look, or I'm trying to understand in terms of like can we set up FTIR, UV, Viz, Raman, and I think we'll have some interest in those, but quantitative NMR might be the easiest one to stand up and the most universal. And we'll see later some other advantages of quantitative NMR versus the other ones. So just I want to give a brief overall showing of what the QMR principles of workflow are. So the intensity is the area of a peak is totally proportional to the number of nuclides, and it's and to some degree a ratio of the purity of things. So we can compare the intensity of two peaks. If one is a standard, then we can very readily identify the number of nuclides, the mass of one component versus the other. So a general workflow is you might have some crude sample. You'll take an aliquot, add to a vial. You'll get a sample weight. Then you'll add some degraded solvent, get another sample weight, and then we'll have our NMR solution. And what we've been using is the internal standard of the residual proteose solvent. So we can take other standards and we can quantitate what the internal standard should be, and then it's very easy to use that to now have the proteose solvent be the internal standard. So you might say, well, how useful is NMR? Like things can get pretty complex, especially with crude mixtures. This is a sulfonylation from one of our benchmark reactions. We have pyridine in there, sulfonyl chloride, aminobenzonitrile. We get this product. One of these is in excess. It's in DCM. We do some evaporation. But you can, for most of the peaks, you can get a clean analysis relative to the DMSO peak. This is in deuterated DMSO. But if we wanted to do some understanding of what peaks were what, you can look at 2D peaks to understand what peaks we're actually calculating. Another way that we're doing it is we're generating reference libraries of the starting materials. So we've obtained Proton, HSQC, GCOSY for each of the stable reactants, reagents for the reaction benchmarks. So for example, this carboxylic acid here in this amine, and then when we do the amide coupling, we can do some comparison, right? And we have some plan to extend this to other known reaction byproducts like hydroxyazobenzotriazole, which is the known byproduct from hot 2 reactions. One of the problems that we encountered very quickly was, in the end, we have a spectra that involves a lot of manual integration. And when you realize that the phasing and the baseline correction is something that they require you to do it manually, and that's not really repeatable, nor is it generalizable to untrained people. So we started looking into different ways of determining the amplitudes of peaks without the normal integration method. And the 3 ones that are out there are Craft, which is, they like, Mestranova offers a global spectrum deconvolution. And then there's a third one out there called Batman. But in terms of how Craft workflow works is that, you take the FID, you can break it down into subregions, and then you can, using filtering, separate the main FID into sub-FIDs. So these are all for different spectral windows of there. And then using some computation, get a complete list of all the peaks with their frequencies, their amplitudes, and their width. So from that, it's very easy to calculate relative amplitudes, and it's something I'll highlight a little later. You can create fingerprint chemical shifts. So the sort of computational power behind Craft is Bayesian estimation of spectral parameters, and there is an open source toolbox offered by Larry Bretthorst at the University of Washington University in St. Louis. From that, what we can do is we can do, like I mentioned, you can take a spectrum and you can break it down into frequencies. You can get estimates of the errors of how it estimate the frequencies. The decay, which is a measure of how broad the peaks are, its amplitude, and also its phase. I don't have the phase showing. And then, from these, what you can do is you can model the peaks as their own sub-FID. So here on the right, I've shown in the back is the actual crude spectrum, and then all of the peaks found by the Bayesian toolbox that we've set up here at NCATS. You can deconvolute into all the different sub-peaks, or sorry, all the different peaks here. And so it identified over 80 different peaks, but for all these, there is an like I mentioned, a frequency, an amplitude, and a decay. So why is this helpful? Well, we get an increase in resolution as a result of deconvolution using this Bayesian process. So, for example, in this amide coupling, a methylene is really shows up as this pseudo quartet here, but that's in a normal integration mode. Actually, maybe I need to. Is there a laser pointer here? Right? Spotlight.
Right click.
Here, can you see the arrow?
Yeah.
Oh, that's an annotation. I thought there was a laser thing.
There's on the right, if you right click.
Right click.
On the PowerPoint. Yeah, right click. There you go. No, go
there,
right click.
There you go.
There you go. There.
Yeah, sorry. Sorry. So this quartet here is, it's relatively obscured by this broad peak. But the Bayesian estimation very easily can separate those 4 peaks from It's a broad peak. And so, sorry, let's go back here a second. So the important thing is that now we can select peaks based on their location, not just by integrating over a region. So if I select, if I have a filter that asks for the amplitude from, somewhere in between this peak and this peak, it'll select that peak and then get all the amplitude. I don't have to worry about whether there's an overlap with an adjacent peak. So we can think about this as a way of digitizing NMR solution, NMR spectra, right? So we now have also a two-dimensional way of representing things. So there's a frequency, there's also a decay, and then we have the amplitude. So, this is just the one on the right is just a zoomed-in version that is removing this very broad peak up here. And that should help with both identification, but it'll also help with quantitation, because we'll be more sure about what we are quantitating going forward. Let's see. So other ways that we are looking to address some of these challenges of assignment is using sliced 2D NMRs. So if you use a DOSI, which is shown here on the right, this is a diffusion ordered spectroscopy. So you can do a virtual separation based on their diffusion constants. So from that, you can identify all the peaks that are consistent with one species. Other ways that we're doing it is ultra-fast 2D NMR techniques like GCOSY and Z-Toxy, which if put together, you can accomplish in a very short period of time. And then once we have a better handle on how to use craft in one-dimensional, it is possible to use craft with 2D spectra and do direct integration of 2D peaks and things like HSQC. I think one thing that I'm also very excited about is, when we combine the 2D NMR methods with like deconvolution like craft, it definitely opens up towards some fully automated processing of results. So not just of, say, the product, but you can look at all the side products. And hopefully this automated assignment allows for ready generalization to non-benchmark reactions. I'm just going to mention this as an aside. QNMR is something that can complement other analytical methods. So we're going to use this to provide calibration for high throughput microfluidic HPLC data. And we also, in some future, hope to extend it to Raman and FTIR. So not to take too much more time, just some acknowledgements. I'd like to thank the Aspire team, engineers, building support, and many others at NCATS that made this all possible. Thanks.
Thanks, Colin. I think if you there are questions, I think you can post them to chat and they'll pop up in our breakout room.
Okay.
We'll see. Thank you for the great talk, Colin. So I see you've got craft up and running now. What are the next steps involved with that part of the project?
So one thing that I've been working on is just been writing some Python scripts that will allow it to be processed more automatically and make it more interactive. Unfortunately, the Bayesian toolbox itself is it's a bit dated. It was created in 2014, and it's something that is not readily updatable, although it provides all the features that you need. It just, there isn't, at least there isn't a publicly facing API. I'm sure that's something that we could could look into. There is some commercial software that that offers a lot of makes available all the workflows that go prior to the Bayesian processing as well as after the Bayesian processing, that just make things more efficient and more straightforward. And that's something that we're going to talk to one of the vendors next week about.
Okay. So there are a couple of questions here kind of related to throughput. One from Sam Patnaik is, what's the expected scale and throughput?
Expected scale. Well, I mean, the throughput, if you have, if your experiment set is, say, takes 15 minutes, which is totally feasible, we're thinking, close to 100 different things you could do, 100 different samples you could do in a day, right? In terms of spectrometer time. Yeah. One thing about the calculation is that it can be parallelized with the Bayesian stuff. So that's something that is easily available to scale.
Yeah. And a question here from Rick: in the process of high throughput medchem, when would it be an optimal time to use QNMR?
So, I think one of the things is, I expect us to answer a lot of questions with the integration of how we're doing the high throughput medchem. In terms of the actual workflow, this is where I think pairing it with UPLC will be important, right? So like it's very difficult with LC methods to know a priori what the response factors are for different species. So with UV-Vis, you can get areas, you can get ion counts, but how the different species have their what the response factors are in the context of those can be totally variable. So you really have no idea whether you're accounting for all the mass that you think of for different products and side products. So QNMR offers the opportunity to give you those results outside of response factors, and then once you have an understanding of that, you can take the NMR solution and do a calibration of things like UPLC. And it's something where you can even the way I think about it, I've thought about it in different ways. You could do it with starting materials. You could do it with purified product. But maybe the best way is to look at your results from UPLC, and you can understand which are the vials that have the most amount of side product, which are the ones that have most amount of in terms of relative amounts, most amount of side product, most amount of product, and then you can do QNMR on those to give good calibration for those particular materials.
Great, thanks, Colin. I think in the interest of keeping on time, so we get to the next session on time. There's maybe if any other follow-up questions can maybe be answered in the chat as we move on to our next speaker. Mark, who appears to be in the lab next to mine, is going to be giving our next talk. Mark joined us at NCATS, what, about a year? How long? Can you remind me, Mark, how long? It's a year and a half now? More? Something like that? Oh, you're muted, Mark.
About 1.5 years ago, yeah.
That's what I thought, yeah. So what's interesting is Mark has actually been stationed out in San Diego. If you had listened to Sam Michael's talk yesterday, we have a really interesting collaboration going on with Stratios Lilly in San Diego with the new automated lab they're building there. And we've set up a collaboration with them to help if you will, characterize and optimize some of their core incubation platforms. In this case, it's this Indigo incubation platform, which is fairly new to the industry in general. And Mark's been very active in that project, and he's going to be telling us some of what's been going on there. So Mark, I'm going to turn it over to you.
Thank you, Alex, and thank you, Sam. So I have been working in Eli Lilly Automation Lab for about 1.5 years. And in this period of time, I got a chance to learning more about the Indigo Reactor, also learning more about automation synthesize. So today I'm going to talking about the development of Indigo Reactor for automatically advanced chemistry synthesize. So in this sector, we're going to learn how I testing the machine, how I took the machine, how I getting this Indigo into the performances can be satisfied all the chemists to use. So in the beginning, I'm going to ask the question for everyone, or it's for all the chemists, how we can execute a reaction. And if we want to execute a reaction, how can we set up the reaction easier and quicker? As the Christopher in earlier the section today talking about, the chemists didn't change much since the beginning of the industry, and how we can run the reaction condition as designed as the condition where one is performed, and how to get the reaction result reproducible every time for the repeatable result. And before we knowing something about the Indigo, I wanted to trace back to the history of the chemistry incubator. So even for a very simple reaction like the heating reaction we want to running in our lab, if you use by the traditional way, it's going to involve a lot of glassware. It's going to involve a lot of resource like the heating, like you need water, you need a condenser to cooling the condenser. Everything will be set up by human being, by the chemist, and it's only one-time use. After you use that, you have to disassemble them and wash them again. Also, for some more complicated reaction, you need to be involved more device. You have to introduce like the gas argon for the gas protection. You also need the thermometer to monitor the oil bus, the water bus, or you want to monitor the internal temperature for your reaction. And also, if you want adding something in the middle of your reaction for a reactant or catalytic, you have to be setting by the reaction and monitor them in the real time. It's not only take the time, it's also take a lot of effort for chemists to doing that. So in the recent year, we have a new technology involved, and like the biotouch microwave reactor. It helps us a lot with the everyday reaction. It can be programmable. It also can be running automatically. But there's a problem also here because it's only one reactor inside of each one, the biotouch microwave reactor. And also it's only running heating reaction. You cannot adding any reactant in the middle of the reaction. You need to stop the reactor and cooling that down and bring back to your hood and adding something else and then bring them back. It's not only not efficiency, it's also going to influence the result for the reaction. So here we have introduced you the Indigo reactor. So what is the Indigo reactor? Indigo reactor have 8 parallel channels with the independent control for heating, cooling, steering, and the reflex for reaction. So here in the first row, you're going to see this is the reaction zone, and the different colors adapter represent to different vial size. So on this side, you can see the blue one is represented to 2 to 5 ml microwave vial, and the golden one is represented to the 20 ml microwave vial. In this case, each one of the reactors here can be interchangeable. It's not necessary using only the small size one. You also can use the medium and large size one. So that's the great part of the Indigo. And you also have this part here. This arm can be closed the reactor, so it can be sealed for the pressure reactions. So other functions like the reflex for -40 degrees. Also, we can heating and cooling that reactor to -40 degrees and raise the temperature to 150 degrees. And also we can control the steering speed for individual line of the reactor and the pressurization for each one of Indigo reactors. And also we can vacuum them down to 300 MBAR for a vacuum scenario. Also, as the reactor, we can auto cleaning the reaction. We can auto cleaning the reactor after the reaction finish. So chemists don't have to worry about any cross contamination after the reaction is done. The automation system will be cleaning itself after the reaction finish. So here we're talking about a lot of functions. And we can see this is the mobile card we are currently have in the San Diego Eli Lilly L2S2 automation lab. And this is the mobile card for Indigo. There's a lot of lines you can see. This is the utility lines providing a lot of functions here, like the high pressure nitrogen, providing the pneumatic power for closing the lid, closing the arm. And the compressor, the high pressure nitrogen is providing the pressurization inside the reactor. And the compressed dry air is providing the pneumatic power to close the reactor and seal the reactor. And also we have the acetone, water, and waste line for all these cleaning circles. Currently, since we are using a mobile card, the pressure acetone is put inside of this null pack, been pressurized, so we can use that as a source for cleaning. And then in the most important part is in the center, we have this Indigo reactor inside of here. It's about the size of 2 microwave reactor, because right now you only can see the top of the reactor. The most other part will be inside here. But if you're putting that into your regular ventilation hood, they'll be about this tall as this high, and it's also save a lot of space. And the last but not the least is the HMI unit. That's the brain for the Indigo. We use the HMI unit to send out all this command, all this recipes running the reaction. And here is the control unit, the modules or function behind the Indigo reactors. How we can achieve all this function, and everything is starting from the HMI unit here by sending this API command to running the reactions. So after the API command sending out, we have the auction box to running all the resource we have here. Either it's going to be pressurizing or it's going to be heating, cooling, all the effect will be controlled by here. And also we got this chiller unit on the side. Probably I didn't mention that earlier. You can see here, there'll be this chiller unit. All this cooling effect is provided by this chiller unit. It's a separate unit. So the limitation of the cooling will be limited by your chiller. If you got a better chiller, the limitation of the cooling and reflex probably can be even lower. So currently we have this chiller, the maximum low temperature we can reach is -40 degrees. And also we can get a close look of our adapters here. And you can see the adapter is separated by 2 parts. The bottom part is for the thermal zone for heating and cooling the reactions. And the top part is for the reflex. They are divided by this white color here. So the thermal will not transfer from one section to another section. And interesting, we found out in our reaction experiment, if you're running a heating reaction, we don't want to fill these vials too high because there'll be interfered the cooling effect here for the condensation. So for that reason, we're just setting up lower volume of our reactor for 3 mil for the 2 to 5 MRV vial. And for the large one, we're just setting up to 12 mil for the 20 mil MRV. And also for the reason of the heating, we have this setting. But for the cooling, we don't have to worry about that because everything here will be cold. Even the reflex zone will be cold, so we can reach out the max of the vials. So everything we're doing here is not only testing, we're also trying to get SOP, and we're also trying to learn more about this reactor, how the function can getting us the result, the performances we need as a chemist. So here is the 4 basic function we have here. It's the heating, it's the cooling, it's the pressurizing, and the steering. So it's very basic 4 function there. But with these 4 functions, we can achieve a lot of reaction conditions. Like the sum of the reaction, we can just simply heating the reaction or cooling the reaction. Or for some other reactions, we can heating the reaction first and cooling them later. And some of the other reactions, the reverse, cooling first and heating them later. And also we can change the steering speed to accommodate different viscosities reaction mixture. Some of them can dissolve very well. We can use lower steering speed. Some of them dissolve very well, or they're like the gels, like the reaction mixture, which is higher RPM. And also we can run the reaction under the pressures. That means if some of the solvent we're using have lower boiling point, we can just raising up the temperature to make it higher temperature inside the reactor, even it's above the boiling point. And also we can running the reaction for the inner reactions under the nitrogens for any oxygen sensitive or moisture sensitive reactions. And another thing we want to mention about here is another technology they call the PIN or small. That technology is being used developing by the ChemSpeed. And by using the pin, we can start the reaction at any critical time by reduce this byproduct, or we can set up the reaction keys. We don't necessarily have to run the reaction at the moment we disassemble or the reaction. We can leave the keys over there for some certain times we want to run the reaction. Also with the pin, we can quench the reaction after it's finished. So here is a close look. What is the pin? So that's the thing I like most. It's the two technology working together. We have the indigo reactor, we have chem speed, small, and we also call it pin. And that two technology working together, making the reactor better perform. So as here you can see, we got this ambient glasses ambient tube here. So in the beginning of the loading, which is loading this chemical reactant or reagent inside here, it can be a solid, it can be liquid. And then we have the laser pore beam to seal this ambient under the nitrogen protection. So everything here can be stored longer time because it's under nitrogen. So avoiding any oxidation, any moisture contact or compound. So you can put inside of your hood or your chemistry bin for later use. I always make a lot of them. And here you can see after the pin has been making, I can easily reassemble them together by putting the pin into my reaction mixture. And after I raise the pressure to 6 bars, the pin will be break. So currently we are saying we are having the pin with 6 bar breaking rate. Theoretically, ChemSpeed is developing some other pins can be break at 15 bars, 20 bars, 30 bars. So by using different pressure, we can break the pin at different time and utilize this function with the indigo reactor. We can introduce all this chemical reactant in the middle of the reaction with different time. So that'll be crucial and essential for our reactors. And here is an example I'm going to show you, and you can see this video here, how I'm loading a reaction. So this is the AMI coupling. I just loaded this how-to pin into my reaction mixture, and then insert this reaction mixture wire into my adapter. I loaded that into the reactor. After that, I just go back to my computer because I'm already writing a recipe, and we'll talking about the recipe later. The recipe is ready there, so I just click the start button, and you will see the arm will be extended from the indigo reactor, and it's happening any moment right now. So it's extend the reactor arm, and right now it's going to close the lid. So from this moment, the reactor is totally sealed and is running automatically by itself. The chemists don't have to, monitor the reaction at all. It can be running by itself. No matter how complex the reaction is, it can be accomplished after it's finished. So after 2 or 3 hours, you can just come back here and pick up your reaction. So by testing, by running, so this is like the testing and tweak we wanted to do before we got the performances. So as we know, we all have these 4 functions. We have the heating, cooling, we have the pressurizing, we have the steering. So we're going to testing all the functions. At the moment, for thermal, we're going to testing the heating and the cooling at the same time. So we use this different solvents across the board. And you can see here, we use 10 kind of solvents. The reason why we use them is because they're across the board with the different thermal capacity and with thermal conductivities. So this way we can testing more broadly for this common solvent used here. So there'll be like total solvent test we're using, and 2 wild sites. We have the 2 to 5 ml MRV and the 20 ml MRV. And for running different temperatures, we're running 5 tests. And since there's 8 reactors, there'll be total 800 for 1 heating test. And for cooling is the same 800 reaction test. Total is 1600 of the test. So why we are running this test? We want to know the thermal profile. We want to know the temperature we're setting for. It can reach the temperature we desire internally, the real temperature, or how long the temperature can reach and how fast the temperature can reach. And then as the same thing with the cooling and how efficiently the cooling can be and how low the temperature can be matched the settings. So from all these 1600 reactions result, and we come out a better understanding of our reactors. And here is the temperature offset we're getting from this result. So you can see here, we have the purple line representing the boiling point for each of the solvent we are using here. So at this high point, we can see each of the solvent we are setting to the boiling point. And the blue line here is the real temperature. So we use a thermocoupler probe and insert that into our reactors, getting the real-time temperature inside the reactors. And we can see that always been offset, always been a difference. The temperature inside the reactor never can reach that temperature we're setting, but it's fine because we have all this data. We can use this data and then learning why it's not happening, because there is adapter. So remember, the thermal energy is going to be transferred from the adapter into the vial and then into the internal of your reaction. So by learning all this data, we're getting the result for offsetting this temperature setting. So currently we got this 12 degrees offsetting. So the chemists don't have to worry about that. That'll be built into our software later on for this function. So when you're setting 100 degrees, the system will be automatically raise the temperature to 112 degrees. But you are not seeing that because it's all behind the scene in our setting. And what we are knowing is the temperature you're setting will be matched exactly, or as much as possible, exactly the real temperature inside the reactors. And for the cooling effect, because we are using a different cooling method, it's a chiller, it's providing much more capacity of the thermal capacity for the cooling effect. The most of the testing we're doing is a match. So the setting we're setting is -20 degrees for most of the solvent, and for some other like dioxin and DMSO, because they have higher boiling point, melting point, which is setting to their melting point. But you can see in this chart, most of the setting can be matched the internal temperatures. So that's a great thing. We don't need to do offsetting anything at all. So this one, what we were talking earlier, we need to testing them and tweak them and make it function and perform as we desire. And here is the same thing as the reflex. How we can see how efficiently the reflex it be in a systematic way and more scientific way. So here we can see after we put the reaction mix while into the reaction, after it's cooling in this reflex zone, we got condensation built up here, but we don't know how much the condensation, how efficiently, how robust the result is. So in this test, we just loaded this MRV with 3 ml of the solvent we are choosing from different testing earlier, and then we pre-weighed it before we're heating them to the boiling point. After we're heating them to boiling point for 4 hours, and we choose the reflex is -20 degrees, and then we're cooling them down again and put them out of the reactor and weight them again, and we calculate the weight loss. So here in this chart, you will see the low boiling point acetone have the most weight loss. It's about 0.21%, and the lowest one is toluene and DMSO is only 0.02%. So it's not going to be significantly decrease or influence our reaction mixture. It's not going to influence our concentration of the reaction. So the result is pretty satisfied. And you probably also see why the reason we choose -20 degrees here, because we're also running a lot of tests. We're running -10, we're running -4, -5 degrees, or even 0 degrees. They all come with different results. So we choose the best, scenario for our reaction conditions. So all this data is recorded in our database. So if you're running a reaction with different reflex temperatures, the things will be a little bit different. So here is the stirring speed we're testing here. And you can see the first one we're saying is the reaction mixture is all dissolved in the vial. So it can be stirring at a lower speed as I talk. And this one is like gel-like reaction. It have to be stirring at higher RPM. So what we're trying to do here is we are going to be limit the function, or limited the efforts a chemist have to do by doing all this research. We're going to learning what kind of mixture you using, what kind of RPM. So when the chemists are running this reactor, they don't have to be guessing what RPM they're going to use. So we're going to give the suggestion, we're going to put it into our setting. If you have the viscosity higher reaction, you can use higher RPM. And here is the pressure testing we are doing here. It's testing the pressure for break the pins. And you can see the pin is breaking at 6 bars, but it's not always that way because the pin is being rated at 6 bars, but there's always been like a little fluctuation between the 6 bars. So at this point, we're setting overshooting about 1 bar for this functions. So before we're doing the offsetting, or with overshooting the pressure, we cannot achieve 100% breaking. But by adding one more bars to our settings, we can achieve all the time the pin break successfully. Also, we can maintain the pressure inside the reactor over 1 hour without any decrease of the pressures. So this is the testing we have been done for all these 4 functions we're talking about. And the last one we're doing the test is cleaning circle. So why we need to cleaning that reactor? Because we don't want cleaning them after we're running the reaction. We just want the reactor be clean all the time, always be ready for chemists to use. So here you can see the reactor have 2 vials here. The first one is our reacting zone, and the second one is our wash section. So after the reaction finish, the arm will be retrieved and the lead will cover this area. And in this part of the vial, we have this tiny little hose, if you can see here, and this is a jet spreading point. We got pressurized water connecting to the system, also the pressurized acetone. So both of them going shooting out from here into this area. For testing them, we just use some jam and to block the hose, because there are 2 very critical parts we want to be clean. The first thing is the black rubber cells we see disconnecting the vial directly. So there's a fair chance it's going to be contaminated. And also the port. The port is for transfer our vacuum and the pressure into our system. So that'll be what we want is be blocked. So in this testing, we use some jam, we use some how-to, and the workflow we're building up here is cleaning with the water and cleaning with the solvent. Here is the acetone and soak with the solvent and drain the waste. And after that, we drop the lead. So it looks like pretty straightforward how we are testing that, how we can tweak that. So actually this cleaning circle take us about 1.5 months or almost 2 months to get correct, because like how long we want to wash with the water, how long we want to wash with the acetone, and how much the volume we want to use, and also how long we want to soak the solvent into there, and how long we want to drain the waste to make sure it's dry inside there. So all these parameters have to be testing and then optimized. So luckily we got this all right, and currently washing circle is only takes 90 seconds after the reaction finish. It's a very robust result. And here we want to talk about the GUI software, the web server software we're using currently. And at the beginning of this testing, we don't have all this good softwares. We only have this Mongo database. So everything, if we want to running the reaction, we have to using this Mongo database, update the database with the parameter we want for reaction. And it's not very intuitive. Also, it's easy to make a mistake. You have to be familiar with the system. You also have to be familiar with a little bit of software. So we come back with the better version of software. We call it the testing GUI software. In this part of the software, we have more function visualizations. We can running all the functions and testing them one by one without learning too much. So the learning curve is much less than the first software we're using. But there's still drawback. If we want to running some recipes, it means if we want to running some automatically complex reactions, we still need the Mongo database to running that. For fixing that, we come with the third version of a software. We call that the web server GUI software. And this software use a web server to connecting the reactor. So you don't need to have the HMI unit. You just need a computer. You connect that to your web browser and input your IP into the Indigo IP address, and you can connect into the Indigo. And in this version of software, we can have more control and more visualization for our reactors. We can see the real-time temperatures. We can monitor the pressures, steering speed, and the status of our lead and the arm. Also, we can know how long the reaction has been running and how many times we still left it there. So we can start the reaction automatically with the recipe. Also, we can export all the data we're accumulated through time through a text file or CSV file. And there's all this log file for all this function it's been using. Also here you have the plot to monitor the real-time temperature and the pressure. And most importantly, after the reaction finish, you can pour out this database for your record into the ELN. So here is our recipe writing, how we can write a recipe. So as I said earlier stage, we have to use the API, we have to use the database, Mongo database to writing that. It looks like not very good here. So we have to transfer that into our better software version. So currently we have one. So give us easier control here. It's easier to understanding for chemists how we can run in the reaction, how we can set up the parameters here, the reaction times, how can we easily reading here. So back to here, we got some decision trees we're showing here. When we are trying to writing a recipe, how we can achieve that, how we can learning what kind of recipe is right or not wrong, because we have the reaction conditions and we have the recipes. There always be a gap between these two. So we're trying to limit, shrink the gap as much as possible. So in the right side, you can see if we wanted to run in the reaction without a pin, that'll be easy and straightforward, because we will only need to set up one parameter for our reaction. That'll be the temperature, the pressure, reaction times, reflex times, and excitation speed. Since the reaction without using any pins, all the parameter will be the same from the beginning of the reaction to the end of the reaction. But if you want to run in something more complex, we're going to introduce the pin. And with the pin introduced, we're going to set up at least two reaction conditions. The first condition will be before the pin breaking, and the second condition will be after the pin breaking. And for our Indigo reactor, we have capability to running 8 set of parameters. That means we can break the pin or we can increase the pressure 8 times. Is that necessary? It's not necessary for break the pin, but it gives us the flexibility to running 8 set of parameters. So remember, in the whole period of your reaction, you can change 8 times. That's quite a lot for now. We probably don't need that much, but they'll be very useful for a complex multi-step reaction if we wanted to introduce multi-pins inside there. And here is an example of the recipe writing. So I call it shopping cart. So basically, you are setting up the timeline for your reaction at the beginning and the stop. So you have your reaction times. After that, you're just setting up the temperature, the heating, the cooling, the pressurization, the reflex. Everything can be set up at certain time point. The time point is very important for our recipes. As I said, we have the same reaction conditions, but if the different camps running the reactions, they're probably putting the reactant at different times. The time cannot be very precise for the human action. But with the recipe, everything can be very precise. We can decide which minutes or which seconds we want to dispense, we want to break the pins. All this function, all the temperature change can be very precise. So that can make sure our reaction can running again repeatedly without any issues. And the result also can be very reproducible. And also the most important function we have here is sampling. And through the whole time of the reaction recipes, you can decide when you want to sample your reaction. You just need to manually click the button and the reaction will be automatically lower the temperature and the pressure into the safe point and open up the reactor. Remember, our reactor can be super hot, can be super pressurized. So for the safety reason, everything will go back to ambient pressure and ambient temperatures. After that, you can sample your reactions, but you don't have to worry about you stop your reaction there. It's going to be resumed after you finish your sampling. The condition will be back, the timer will be kicked back again. So everything will go back again automatically. You don't have to worry about the time it's already using in the future. So here I'm going to use 3 very common reaction example to showing how the recipe be writing and how we are monitor the reaction recipe be perform as it's supposed to be. And also we're going to learn the logging file system, how we are running this. So here is the AMI coupling we are showing here. It's a very simple and straightforward one. We make the pin first, as showing here. It's also in this ambient pin. And we load other things like the AMI, the acid, the base, and DMF, all the other things in this vial. And then we just loaded this one here into the microwave vial. After that, we're just loading everything into our reactor. From there, we're going to running our recipes. So what's the recipe going to be? So we're going to starting the reaction mixture at room temperature. And then after that, we're going to pressurize our vial at 6 bars. At that point, you can see we are monitor our pressure system is from 0 to 6 bars and successfully break the pin. After the pin is breaking, the hot will be released into our reaction. At that moment, the reaction is started. So we can control exactly time point when to starting the reaction. We're not only control them, we are also knowing them and can repeatedly doing the same thing again and again. And here you can see after the pin breaking, we sending the recipe command the reactor heating up to 60 degrees. And this is the time we're setting for 3 hours. And after that, we got our COI from the LCMS. It's a successful running. So by setting up these recipes, we can repeat this reaction again and again, and we can get the same result every time.
Hey, Mark.
And
Mark, we're running a bit long.
Okay. So I'm trying to. Okay.
Yeah,
let's go quicker.
Yeah. So maybe just quickly show the next couple of slides and wrap it up so we can try to get back on time.
Okay. So here is another example of Suzuki reactions here, and the Suzuki reaction, we're trying to break the pin at 80 degrees. So we're sending the command, to run the reaction, hitting the reaction first, and then break the pin. And then there's another reaction example we can talk about later is the sulfonation, and we're also make the pin for sulfonic chloride, and you can see we're running very different conditions for that. And here we want to run the reaction to 0 degree first, and then we're trying to, break the pin at 6 bars. And after that, we can just easily raise up the temperature. So this all example showing the complex reaction that Indigo can do. And the reason why we're doing this, because we're trying to get the benchmark reaction done. So as you all see, we're trying to benchmark our reactor. So by running all these reactions in our Indigo, we can benchmark that reactor and tell how good the performances can be. And as designed, there will be about 864 reactions need to be done for verify this reactor. Since we have like 8 lines, we have different concentrations, different scales. So that'll be talking about later. So how can we use the reaction template to help? How can we use the recipe to help us with the reaction template? So here is the example. So when we have the reaction conditions, we can transfer that into the recipes. And then later on, we can use that recipe storage in the ALN. When the chemists are going to running the reaction, they not necessarily have to, going back to the conditions or rewriting the recipes. You can just use that directly. And here is the benefit we running the reaction with the recipe. So how can we make the reaction reproducible with the same Indigo reactor? We're capable of doing that with the recipe. And with the benchmark reaction, we can verify different reactor functions. It means if you have 2 Indigo reactors in different locations, by using the benchmark reaction function, we can testing them and make sure they all have the same function. If we are running them in San Diego or in 9800, we can get the same result every time. And also we can save the time for setting and monitor the reaction. It's automatically running by itself. And so here's the conclusions here. So remember the 3 questions we were asking about in the earlier stage. Is that complete? Yes. So we're saving the time and actual glassware to setting up the reactions. The setting up the reaction time is very quick. It's about 40 seconds if you have everything ready. And also we can run the reaction at exactly same condition repeatedly again and again and get reproductive results. And also we can monitor the system in the real time. Also with the built-in circle, we can eliminate any cross-contamination. So currently the Indigo reactor is ready to run the automatic reaction fully functional here in San Diego. And so for the next part, we're going to increase some functionality or better performances by upgrading our parts. So like the arm, like the pressure manifold, currently we're going to use that, upgrading that into a thin steel coated with the chemistry resistant coating, and that'll be significantly increase the performances of our reactor. Also in the hardware part in the L2, S2, we're already using a robot arm that belongs to another Indigo reactor. It's not the one we're showing in the early stage. It's not in the mobile car. It's in larger platform in the chemistry platform. We already use a robot arm to loading and unloading the reaction while inside the reactor. So that means we can continually running the reaction without any interface. And also the next part, we're going to upgrade our software with better understanding of our UI system, easier for chemists to use. Also, we want to add the barcode function. So for each reaction, we can logging them into our system. And also in the future, probably we can utilize Miguel have the software for the reactions dashboard. If we can, and also integrate this system with Indigo, we can monitor and control them anywhere in the lab. So that's all I have here for today. And great thanks for Alex, for Sam, and for Colin for all the support, and also the support from the Eli Lilly and Stradio Techmatic and MD&E. And give the floor back to everyone if you have the question.
Great, thank you, Mark. I think in the interest of time, let's direct questions to the chat, and Mark can try to address them while we go on to our next talk, which is
Okay.
so to keep things moving quickly, we've got Dave Calabrese. Again, he's a recent hire at NCATS. Has been with us for I guess a year and a half, and most of it under the COVID scenario. So. But he's done a tremendous amount of work bringing up our reaction screening platform. And so with that, I'm going to turn it over to you, Dave, and get things going.
Hello, my name's Dave Calabrese. Thank you for the introduction, Alex. I'm going to try to go quickly through this just for the sake of time that we have left, because I know that there's another poster after me. One of the things that we talk about with reaction screening in Aspire is that we are screening our way to automation, because we really see reaction screening. Oh, I should have my video on. We see reaction screening as a way to bring us forward to automation, and that can provide us a lot of values. This is a slide that Alex showed yesterday, but I kind of want to reemphasize the points that reaction screening is going to help us provide a lot of value for automation with design protocols and templates, not just for setting up reactions and sampling, but also communication between different instrumentation. We also see that this is a great platform to provide synthetic chemistry assistance to directly help users for providing reaction screens, reaction screening kits. And this is also a good platform for collaboration within Aspire between the chemistry and informatics groups. For instance, the informatics groups have looked through the electronic notebooks here at NCATS and determined what are the most common and challenging types of reactions, meaning low yielding reactions that are done at NCATS. And those are the types of reactions that we are going to prioritize for making reaction screen kits for users to use for on-demand screening. And we also see this as a good platform for being able to profile and validate new technology in the automation sector. And we can assess new opportunities to go forward with Aspire. Now to talk exactly a little bit more about reaction screening specifically and how we are automating that process. So the current process for running a reaction screen, if you were to do this manually, and it's very similar with this 4-step process automatedly, would be you would have your reaction setup and execution, and then you would have your reaction data analysis afterwards to process and learn from your data. From your reactions. And I want to tell you about how we are automating each one of these 4 steps and how this is going to improve the speed and efficiency of this process, because you know, if you've run a reaction screen yourself, the more variables that you add to this, or the more like different bases that you're adding to a reaction, it sort of exponentially increases the amount of time that you need to spend on that reaction screen, sort of slowing you down. And if you run a more narrow screen, that only limits the amount of options that you can actually see from your screen. And so we're trying to provide the best of both worlds here with our automation process. And so I want to talk about first about the reaction setup and execution. So the instrument that we're using for a lot of this is the Unchained Labs Junior at the moment. It's capable of liquid handling and solid loading. There are 3 reactors which are capable of heating and cooling reactions and stirring. The liquid handling is capable of using needles to inject liquids or pipettes. And the solid loading also has a balance associated with it, here labeled in black, and that is for weighing the solid out efficiently. And these things can be done remotely. You can set up the procedures and execute them remotely, which was very helpful for us in times of COVID. And there's also a camera that's out of the screen here, so you can monitor what's going on in the Junior remotely as well. Here's a video to show you what's going on, how the Junior works. These are setting up 2 different amide coupling reactions that you can see on the bottom of the screen here. So first it picks up the rack and moves it to the balance. And now it's going to start weighing out the solid. So it picks up the solid loading head and then picks up an individual solid, and then it goes towards the balance. It goes on top, right above the vial that it's adding to. And it adds the solid there. It's now changing out the solid and moving on to the next one. and it'll add this all to both of these reactions. So you'll see at some point it'll lift up and move to the side, and that's it adding to the next vial down the line. Now you will notice that this is a hyperlapse video. It's running at about 8x speed. Some of the solid loading does take some time for that to happen, but you're not running it yourself. You can be doing something in the background while this machine is running. I also want to point out that these reactions that we ran were actually pretty clean, pretty well done. It's also very similar to how these reactions were run when we ran them manually in parallel. And I believe this is the last solid that's adding, so it's now going to lower that arm and pick up the plate moving tool. So it's going to move the plate out of the balance and onto the reactor plate, and it's now going to do some of the liquid handling. So it's going to start injecting the liquids. The first one is going to be DMF that you'll see added here to both vials. And I'll just show this and one more liquid added before we move on. I believe it's the base that's added next. And you'll see that for these lighter vials, lighter volumes, that's actually doing a brush on the side of the vial. So it's making sure to get every the proper volume there by getting the last drop out of the needle. The junior can also sample during the reaction, so you can do a time course. Can take an aliquot of your sample into a quenching solution or into an LCMS vial so that it can be monitored as the reaction is progressing. In concert with the junior, we are using a glove box to support the reaction screen and kit preparation. The glove box is for the air and water sensitive reactions that we would want to run. And there are 3 different reactors in the glove box and a speed vac as well. We also have over 30 different Suzuki and Buchwald Hartwood catalysts to run for reactions that are already loaded in the glove box. So now that I've talked to you about how we are automating the process for the reaction setup and execution, I now want to talk to you about the reaction and data analysis portion. So we have a Waters UPLC dedicated for this project. It does slightly under 2-minute runs for each sample. So if you're running a 96 well plate, that takes about 3 hours to run. So that's very quick to run essentially 100 reactions. To process the data, we're using the Versidian Analytical Studio, which is able to upload the data from the Waters UPLC and process it pretty quickly. Here's a colorimetric graph on the right here, where red is no reaction and towards blue is a higher conversion. The analytical software, in addition to providing you that colorimetric data, can export to an Excel spreadsheet that gives you the ion count and absorption of the different peaks, and it's able to identify the starting materials, products, and internal standards and what have you from your reaction. This is, of course, a more qualitative form of analysis, although in a lot of scenarios that will be sufficient for many people. But QNMR methods, as Cullen was talking about in his talk earlier today, are being developed to determine more precise yields if that is needed for a particular user. And so now that I've talked to you about how we have automated the setup and analysis of the reaction screen platform, this is probably the part that's going to be most interesting for the people who are here in the audience today, which is how we can be of service to the chemists outside of Aspire, so the people in NIH and other institutions. So the first one, as I've been talking about, is reaction screening. If you have a reaction that you don't know the conditions that you would want to optimize or find something that could work, we can take that, we can run that screen or several screens for you to figure that out. Our goal is to get it back to you same day, although we, depending on the certain reaction, it might take a little bit longer than that, but that is our goal is same day, but we're trying to make that quick, because if we can't get it done quickly, then why wouldn't you run the screen yourself? And so that's our main focus there. We also are preparing reaction screen kits, which I alluded to earlier. These are for those more common and more difficult reactions that we are thinking that are going to be the most high volume demands from users. And these are for kits that we can provide with them for on-demand screening, so they can so they could potentially run the screens themselves. If they want us to run the screens, we can do that as well, although that's more of bullet point number 1. And finally, although this isn't a thing that we have done currently, we think that our platform should be really able to handle derivatization of late stage analogs. Because we can run so many reactions in parallel, this really seems like a platform will be able to handle this nicely for users. And so let me give you a little bit more of a concrete example of reaction screens, so that you can sort of get a better idea of what we can accomplish. And so this was a chemical reaction that we were approached by an NCATS chemist with. This reaction was unknown in the literature and was the first step in a multi-step synthesis. And the user really wanted a high-yielding reaction that could be scalable for their needs, as you might imagine. And so we took this Suzuki cross-coupling reaction. We used the junior to add the non-air sensitive reactants and bases. So adding all the solids, we loaded it into the glove box and add in the catalyst and solvents and ran the reaction there. There was 96 different reaction conditions that were explored over 2 plates of 48, changing the time, temperature, and catalysts that were used. This is how the reaction looks like when it's processed in the junior. You can, red again is no conversion, where blue is the highest amount of product. You can see that there, colorimetric wise in the upper left corner, that there are several reaction conditions that do work for this, many reactions that don't, but this means that it's a successful screen to show that. And the one that's highlighted here in dark blue, that's sort of squared off in E7, that's the one that we have the LC trace here for. And so in blue, that's the product peak, and in purple is the starting material peak. So you can see that we're actually getting a pretty good conversion with this reaction. And so this is the data that we would provide the user with, that would be more readable, so they could see the reaction and the different conditions. And what we can see here is that the base is really important, that cesium carbonate and tribasic potassium are really the 2 bases that work with this reaction. And there's a handful of catalysts that also work as well. And the user from this data was able to find conditions that was able to scale up, and they were happy with the screen that we ran. And to talk briefly about kits, we've currently made a kit for amidation and esterification, as we're currently designing and making more kits. But as an example here on the bottom, this is an amidation that we ran using our small amidation kit. What we can see is that TEA is the most effective base for this reaction. There are several different coupling reagents that work for this, but HA2 is the best. And these are available for on-demand use for chemists as well. And with that, to conclude, we have developed an automated reaction screening platform that quickly can provide chemist solutions to their synthetic challenges. We're designing and have produced a few reaction screening kits for on-demand use, and our platform is ready to assist users, although a little bit of an asterisk there that we're getting our pump replaced for our Waters UPLC right now. And so our analytics for data processing this will be up and going soon, but we are ready to go otherwise and help people out with their reaction screening needs. And with that, I'd like to thank the Aspire team, the analytical chemistry team here at NCATS, also the chemistry team who provide the example that you saw here today, and building support who got these machines up and running, and your attention. Thank you.
Thanks, Dave. Yeah, and thanks for the quick run through. I think we've made up a few minutes, so that's great. I guess while our next speaker is getting set up here, maybe we can entertain 1 or 2 questions really quickly.
Sure thing.
If anything pops up on the chat.
This is great. At some point, do you think this can be also, if this happens to be a final step, can you think of adopting the condition and making a library like,
Right,
90?
yeah. So
Yeah.
that's sort of what I was talking about with the late stage, the derivatization of late stage analogs.
Okay, got it.
Yeah, so that's not something that we have done currently, but that's something that I think that the platform is really capable of doing. And so you can apply that derivatization to making a library as well. If you had like a particularly active compound that you want to try to potentially improve or design a large SAR for, or something to that extent.
And if that is the case, and how do you purify, if you have a 96 reactions, right?
Right. So these would be on small scales. And so that would go into something that is it's talked about in a different one for me that talking about the SPE purification that the engineering groups are working on. It would have to be in collaboration with them, since this process for reaction screening isn't necessarily designed for purification of the reaction by itself. So it'd have to be using SPE or other purification methods.
Right.
Thanks.
Mhm.
So one question here, do reactions that require consistent cooling at -78, can they be adapted to automation?
They
Maybe
probably can, but not on our current system. The lowest temperature that the junior can go to is -20. We would need a different system to be able to achieve that, which I believe could be possible, but not the infrastructure that we have currently.
Right. Okay, so in the interest of time, I'd like to move on to our last talk for this session. So if Jagadish, if you start getting set up here, I'll quickly introduce you. So Jagadish is Nagendra Manda is a postdoctoral fellow who's actually working on being sponsored currently by Ganesha Bantakalu, and it's an interesting story of kind of like speaks to kind of like internal collaborative efforts that we get involved with as part of the Aspire team, trying to recruit chemists to work directly with us, and this is a classic example of just that. Jagadish approached us about an interest in using some of the reaction screening platforms we're trying to develop to help develop some of the chemistry he's doing as part of his postdoc project. So Jagadish, I want to welcome you and turn it over to you for the presentation.
Thank you, Alex, for the introduction. Hello, everyone. And so today I'm going to talk about a project that we recently started in collaboration with Aspire Chemistry team. So the goal of this project is basically to develop new chemical methodologies to solve some of the existing unmet synthetic challenges that are relevant in medicinal chemistry and which could have a potential applications in optimizing lead compounds. So the challenge that we would like to address here is N-trifluoromethylation of heteroarenes and amines. So why N-trifluoromethylation? And as we all know, and as we all agree, that nitrogen-containing compounds, specifically heteroarenes and amine functionalities, occupies a major chemical space in current drug discovery processes. And apart from that, the fluorine has pretty significance in drug discovery, and the introduction of fluorine into small molecules can modulate different properties, including activity and DMPK. So, which clearly demonstrated by nearly 340 drugs that are in currently market, which contain fluorine as part of them. So it's considering the significance of fluorine and the prevalence of nitrogen-containing compounds, it is reasonable and rational to think about trifluorination of these heterocycles as a strategy to modulate the properties. But interestingly, not much has been studied so far on this area, and primarily we think because of two reasons. One, the chemical stability of these compounds. So there were concerns in the past about the stability. However, the studies from past 7 years, 10 years so clearly showed that these compounds can be stable and isolable. And when it comes to the synthetic methods, this is the area that really needs more improvement. And so far, the existing methods are not really viable to access a broad scope of N-trifluoromethylated compounds, particularly when it comes to heterocycles. There are very, very few methods that are available. And perhaps this could be a reason why the suitability or the applicability of this N-trifluoromethyl group was not studied in drug design. And so this is the recent study that kind of shed some light on the importance of these groups, and by converting the N-methyl to N-trifluoromethyl groups on these azoles, they showed that how this transformation could impact the biological pharmacological properties of these compounds, and clearly shows the need for studying these motifs further, particularly in other heteroaromatic systems. And the one way to achieve this is to find or develop new protocols to make these N-trifluoromethylated compounds. And when speaking of new methods, which kind of reminds us a study that was published a few years back, and by scientists at AstraZeneca and CVMD Medicines, and which quoted that the current and frequently used synthetic reactions in medicinal chemistry, and none of them were discovered in the past 20 years, except 2. So kind of suggests that the need for new reactions in medchem. And I think it is important to adopt new technologies into medicinal chemistry, specifically to explore the new chemical space that is not possible with current or existing methodologies. So that's the goal. So we would like to develop a new method for trifluoromethylation. So to do that, we want to explore the new reactivity patterns that are vastly developed from the past 10 years using photochemistry and electrochemistry. And so integrating these new methods with the current Aspire chemistry platform and using the resources they have, and such as photoreactors and state-of-the-art electrochemical stirrers, and hopefully a much more automated system which is integrated with photochemistry and electrochemistry. So we'd like to perform rapid optimization so that could develop a new method for this N-trifluoromethylation. And by doing that, we can have a chance to study the potential of these compounds in current drug discovery. So to do that, so this is our hypothesis or reaction design that we come up with. So ideally, we would like to generate 2 separate protocols, a photochemical approach and an electrochemical approach to access these compounds. So the design includes so generation of 2 reactive species, a CF3 radical, and the hypothesis is we can get this either through a photochemical approach from a electrophilic CF3 source via a photocatalyst, or from an electrochemical transformation from a nucleophilic CF3 source and through oxidation by anode or a cathode. And parallelly, in another catalytic cycle, we would like to employ a transition metal catalyst, and which upon interaction with the heteroarenes, it generates a metal complex. And upon oxidation with either photochemical or electrochemical source, generates a high oxidation metal complex. And the idea is trapping these 2 and to generate a copper-3 complex, which upon reductive elimination leads to the compound that we need. So this is the hypothesis and possible mechanism that we have. And to pursue this reaction, a few things that we have in mind was we would like to use commercially available reagents and try to optimize a milder reaction conditions so that we can perform late stage functionalization. So with that idea, we initiated recently the optimization of this reaction. So initial conditions were chosen based on some of the literature precedent. So the initial screen was focused on different solvents and also different ruthenium photocatalysts. However, in all of these, we didn't really observe the desired product that we would like to. However, what we see is a product that resulted from trifluoromethylation onto this C3 position. And even though it is not what we intended, definitely it is something that we can look forward as a new transformation. And at the same time, the formation of this product also ask a question that, is there any background reaction that is involving in this transformation without photochemical activation? So to know that, we performed some control experiments, and without light and without catalyst, without photocatalyst and without metal catalyst. And none of these really didn't yield any of these products. So, which is good in a way that it seems even this product is happening because of some sort of photochemical activation. However, so the current goal is to avoid formation of this and make the trifluoromethylation happening on nitrogen. So so to do that, we can do a rapid optimization or more studies. However, I choose a bit of shortcut way here. I choose a different substrate where I can block this third position and have much more symmetrical molecule. And any trifluoromethylation on nitrogen leads to the compound I need. So studied initially with some electrochemical approach, and I do see some product, but not really a considerable amount. And recently performed a photochemical study and see around 30% of compound by LCMS. And then at this point, by crude NMR and fluorine, it seems very promising. However, further evaluation is needed after purification and analysis. So that's where I am with respect to optimization. And the future direction is, hopefully we would like to use a much more like a 96 well plate to do multiple reactions and integrated with this auto sampler, so which gives a chance to study much more reactions in a short amount of time. And really the big picture that included in this project is to study the biological activity of these compounds. So we designed 2 case studies for this. First one include control studies on ADME properties. So we chose these 3 specific compounds for which the N-methyl analog is already known and the activity profile is available. And each of those have one specific property of the limits. So the idea is here, by making the corresponding N-trifluoromethylated compound, you could have a direct comparison how it influencing each of these parameters. And that's the one study that really would like to do. And second study that we planned was based on this NOx2 inhibitor. So, and this is pretty potent, and however, it has some limitations in terms of moderate to high clearance and low oral bioavailability. So, and the meta-ID studies on this showed that the major metabolite results from the oxidation of this N-methyl and N-isopropyl. So the goal here is to replacing these methyl groups as a sequentially or overall, to make different analogs and study those and see, hopefully we can get a better compound than this compound here. So those are the future directions, and with that, I would like to conclude the hope. So we are initiated a new methodology development with the assistance of Aspire Chemistry, and hopefully in future with much more studies, so we can achieve what we would like to. And with that, I would like to thank the Opportunities Committee grant for generous financial support, and also Aspire Chemistry team for their willingness to collaborate in this project, and analytical team and COMA team for their continuous support. And I'm happy to take any questions. Thank you, all of you.